Once again, I'm your online lecturer, Frank Jacobs, and today we're going to talk about numerical descriptive techniques. Here we go. We recall that in chapter 2 where we use graphical techniques to show the relationship between statistics marks, business statistics marks, represented by a histogram as shown here. And I didn't mention that the scale, it is an offset because of the little flaw in the software. It's not as Lotus 1, 2, 3 where you can get this. This should be shifted by this much. So this point should be 50, 60, 70, 80, 90, and 100 should be out here. Okay, this is just graphically showing you the business statistics marks. So we say, why the histogram provides new insight. Other interesting questions we need to answer. What, for example, is the class average? What is the spread? What is the spread of the data? These questions go unanswered, and we have to go in detail into more numerical methods for explaining our data. Numerical descriptive techniques, we look at, in summary, what we are about to do, what we have to do in the future. This is like the course objectives. We look at measures of central location, and that would include the mean, the median, and the mode. And then we look at measures of variability. We look at the range, the standard deviation, the variance, coefficient of variation, and measures of relative standing, percentiles, and quartiles. These are some of the ideas. Measures of linear relationship involve covariance, correlation, and the least squares line. That will cover chapter 4. Measures of central location, we do the first one. The arithmetic mean, also known as the average. And sometimes we just use the term mean. This means the same thing. As I say, it's the most popular and useful measure of central location. And it's computed simply by adding up all the observations and dividing by the total number of observations. This is shown here. Mean equals sum of observations divided by number of observations. And a note and notation for this course, when we refer to observations in a population, we use the uppercase N. When referring to the number of observations in a sample, we use a lowercase n. The arithmetic mean of a population is denoted by the Greek letter mu, as shown mu, and the arithmetic mean of a sample is denoted with an x bar, bar with the x. And this is shown summarily. Population sample size, a big N for population, small n for sample. This is the mean, and that is x bar for the sample mean. Shown mathematically here is the same thing. The population mean is shown as sigma, meaning sum. The sum of all the values of the observation. You're summing I equals 1 to n, you're summing n observations, and then you divide it by total number of observations. The same obtains here when we're talking about the sample mean. X bar equals the sum of the x values over I from 1 to n. You're summing n individual observations and dividing by the number of observations. Again, we see pictorially this thing in a nutshell. Sample size, the population sample size, the population mean is shown here as what we see just on the overleaf, and X bar is shown here. The arithmetic mean is appropriate for describing measurement data, individual, or what you say, interval data, the same thing. Heights of people, marks of student papers, etc. These are examples of interval data, or as the term is used, measurement data. Interval data is better. Note that the arithmetic mean is seriously affected by extreme values called outliers. As soon as a billionaire moves into a neighborhood, the average household income increases beyond what was previously. So the large figure is going to cause a skew, and the mean moves in the direction of the skew. Measures of central location, the median. The median is calculated by placing the observations in order. So you have to order the observations first. And the observations that falls in the middle is called the median. Now, this depends on whether you have an odd number of observations or even. In the case of an odd number, it's clear how to find the middle. In the example shown here, for example, you have 0, 7, 12, 5, 14, 8, 9, 22. So you have an odd number. Ordering them looks like that. 0, 0, 5, 7, 8, 9, 12, 14, 22. Which is the one in the middle? Obviously 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 8 is smack in the middle, 8 is the median. Right? In another case where you have an even set, as shown here, 0, 7, 12, 5, 12, 14, 8, this set of numbers, you have 10. So how are we going to find the middle? The middle is going to be occupied by two numbers. So you're going to have to find the mean of the middle two of an ordered data set. As shown here, you have 8 and the 9. So to get the median, you would add 8 plus 9 and divide by 2, giving the median as 8.5. Right? Sample and population medians are computed the same way. Note. That's the median. Measures of central location, we continue with that. The mode. The mode of a set of observations is the value that occurs most frequently. That is the value with the highest frequency. A set of data may have one mode, or a modal class, or 2 or 3 modes. As we said, that the mode is useful for all types of data, though mainly used for nominal data, which we had covered before earlier in our course. For large data sets, the modal class is much more relevant than a single valued mode. So in terms of lots of data, you use the modal class. You group your data into classes and you use the modal class. Sample and population modes are computed in exactly the same way, right? No differentiation. Now, our mode, an example. Look at our data set here. 0, 7, 12, 5, 14, 8, 0, 9, 22, 33. You have 10 observations. Which observation appears most often? Obviously, it's 0. So the mode is 0. How is this a measure of central location? Is something for you to ponder on. The mode. Okay? A diagram is shown here. Is a histogram, and you see the class with the highest frequency, that refers to the modal class. Right? That's all for the mode. Just a note in Excel, equal mode range is how you acquire the mode. Equal mode, open brackets. You highlight the range and it gives you, but what Excel is telling us is that if we're using a data analysis and our data are multimodal and there's more than one mode, that Excel only calculates the smallest mode. Okay? So you can apply other techniques, for example, histogram, to determine if the data is bimodal, trimodal, etc. Now let's look at the mean, median, and mode in a distribution. This is a symmetric distribution. It's called a bell curve, bell-shaped curve, or normal distribution. In this case, the mean, the median, and the mode coincide, but it's drawn here separately so that you can actually see the division, but they do coincide. Mean, median, and mode for a symmetric distribution. If the distribution is skewed, as I mentioned before, that the mean moves with the skew. This is a positively skewed distribution, and you've learned what a positively skewed distribution is, so we won't review that. Here, the highest point, this line would be the mode, that would be the highest frequency. The median is in between, and of course the mode, the mean moves with the skew. It's positively skewed, so the mean is in the direction of the skew. If it were negatively skewed, then the mean would be closer to the skew, right? Mean, median, and mode again. If data are symmetric, the mean, median, and mode will be approximately the same. They will be theoretically the same, but that's only theory. In real life, you don't have that. If data are multimodal, we are asked to report the mean or median on a mode for each subgroup. For each subgroup, you report the mean, the median, or the mode. If data are skewed, report the median, because the median is not affected by skew. It's only the mean is affected by skew. Right? That speaks to the mean, median, mode. We're looking at the mean, median, and modes for ordinal and nominal data. Ordinal and nominal data. For ordinal and nominal data, the calculation of the mean is not valid because for nominal and ordinal data, the values are really categories. And the numbers associated, they are just labels. They are not real data. The median is appropriate for ordinal data. You can find out which is the middle value. For nominal data, a mode calculation is useful, obviously. You want to find out within each category what the frequency is. So you can say which category has the highest frequency. Right? So for nominal data, the mode is useful to determine the highest frequency, but not for central location. Not for central location. We now come to the geometric mean. The geometric mean is used when the variable is a growth rate or rate of change, such as the value of an investment over time, the returns of an investment over time. For instance, if R1 denotes the rate of return in period I equals 1 to n, then the geometric mean denoted R sub g of the returns R1, R2, n is defined such that, and you don't spend too much time trying to figure this out. This is beyond what we cover in the class. All you're interested in is this, the result, which states that the geometric mean of n rates of return is obtained by finding the nth root, written that with an n here, the nth root of 1 plus R1 times 1 plus R2 times 1 plus Rn. That is, each rate of return is added to 1, and then the n terms are multiplied, finding the nth root of those n products, and the last thing one does is subtract 1. So this operation has to be done first. Finding the nth root of the product, and then minus 1. That gives you the geometric mean. This would better be demonstrated by, we'll do an example which follows as to the usefulness of the geometric mean, and also an example of how to do this. We're looking at a finance example. Suppose a 2-year investment of 1,000 grows by 100% to 2,000 in the first year, but loses 50%. So it goes from 2,000 back to the original 1,000 in the second year. What is your average rate of return? Right? We're going to use the arithmetic mean. The average rate of return, we call it R bar. R1 is the rate of return in the first year, R2 is the rate of return in the second year. Remember, the first year, the rate of return is 100%. And in the second year, the rate of return is minus 50%. So to find the mean, you add these two terms and divide by 2. And that gives you 25%. It says that this is the mean rate of return. This would indicate that we should have 1,250 at the end of our investment and not 100. So that means this is not showing the picture correctly. We're going to solve this thing using the geometric mean, right? Which is going to yield a rate of 0%, and this is correct, right? The geometric mean is a product of, as I said, this is, you only have 2 terms, so you're going to find the square root. If you have n terms, you find the nth root. So 1 plus R1, one thing you must note is that when you're calculating the geometric mean, the rates of return are given in percentages, you put them in decimal format. So 100 will be just 1. So 1 plus R1 is 1 plus 1 times 1 plus minus 50 is just 50. 1 plus R2. R2 is, remember, R2 is 50%, minus 50%. So you turn it into decimal, minus 0.5, right? So we find the square root of this product. 1 plus R1 is 2 times 1 minus 0.5, which is a half. So half times 2 is 1, the square root of 1 is 1. 1 minus 1 is 0, which gives you the correct picture, right? Correct results. Measures of central location. This is a summary. We're just about winding down now on this part of the chapter. We need to compute the mean. Compute the mean to describe central location of a single set of interval data. Note interval data, real measurement data. And we compute the median to describe the central location of a single set of interval or ordinal data. We compute the mode when we are describing a single set of nominal data. Nominal data speak to categorical data, where the values of nominal data are the actual categories. We compute the geometric mean to describe a single set of interval data. Notice real data based on growth rates, rates of change, growth rate, generally the rates of change. This is as far as we will go in this lecture. And we'll continue the other sections in lectures that follow. That's all, folks. See you in the next class.